Hello everyone. We are now ready to look at the oracle complexity bounds for the subgradient method. Since the subgradient is only defined for convex functions, we will only look at the results for convex cases. Let us begin with discussing the assumptions. Recall that we are considering the problem x star equal to argmin over x in calligraphic x, f of x, where f is proper closed and the set calligraphic x is closed convex such that it is in the relative interior of the domain of f. The two key assumptions are that AC, which is f is convex, and AL, that f is Lipschitz continuous with parameter LF. Of these, we have so far never needed the Lipschitz continuity assumption, and that is the one that is new. The reason we need it is that we require the following result, that if f is LF Lipschitz, then the dual norm of the subgradient G is less than equal to LF for all x in calligraphic x. We have already seen this result earlier. As you will see, this would be a critical component in all the proofs. The projected subgradient method entails carrying out the updates xt plus 1 equal to px of xt minus eta t gt, where gt is a subgradient of f at xt. Unlike the projected gradient descent, we will not be able to establish the non-increasing function value property. So we will not be able to use the optimality gap as a metric. Instead, we will use the best value achieved so far, that is f best of t equal to min over tau from 1 to t, f of x tau. The result is that for f convex and LF Lipschitz continuous, the number of oracle calls required to achieve that the best optimality gap is less than equal to epsilon is given by order BLF square by epsilon square. So here the rate is worse than 1 by epsilon rate that we are used to for the smooth convex cases. Moreover, instead of L, now we have dependence on the Lipschitz constant of the function LF. We are directly presenting the results for projected subgradient, since there is no improvement in rate if the calligraphic x is the entire space V. The first part of the proof, where we obtain the one-step inequality, is very simple. All the complication actually arises in the choice of the step size. Also, unlike projected gradient descent, here we need not define the subgradient map because it does not have all those interesting properties that we had for smooth case. Instead, we will directly write down the squared distance from the optimum. The norm square of xt plus 1 minus x star equal to px of xt minus eta t gt minus px of x star, where we have used the fact that x star is already inside calligraphic x, so px of x star is equal to x star. Now we need to use the non-expansiveness property of the projection operator. We have already seen this property before, and from this we obtain that the right hand side is less than equal to norm square of xt minus x star minus eta t gt. So we are able to drop the projections using the non-expansiveness property. It remains to expand this and use the definition of gt as in earlier, so as to obtain that norm square of xt plus 1 minus x star is less than equal to norm square of xt minus x star minus 2 eta t inner product of xt minus x star comma gt plus eta t square norm square of gt, which is less than equal to, from the convexity condition, that xt minus x star norm square minus 2 eta t f of xt minus f of x star plus eta t square norm square of gt. Let me also write down the right hand side, which is the norm square of xt plus 1 minus x star. So this is the required one-step inequality. So the first step was very easy. Now we need to use this inequality in order to consider and discuss the various choices of step sizes. A remark is that if you remember our discussion with Frank Wolf for non-convex case, we had a similar inequality. In fact, the rest of the discussion would also be similar, and we would get the similar rates also. We begin with the discussion of the simplest case, that is epsilon dependent step size eta. Replacing eta t with eta and taking the telescopic sum, we have that x of capital T plus 1 minus x star norm square less than equal to x1 minus x star norm square minus 2 eta summation over t equal to 1 to capital T f of xt minus f of x star plus eta square summation over t equal to 1 to capital T norm square of gt. Now as before, the sum on the left can be lower bounded by 0. The first term on the right can be bounded by b, and the norm square gt square term can be bounded by the Lipschitz continuity by LF square. So rearranging, we obtain that 2 eta summation over t equal to 1 to capital T f of xt minus f of x star less than equal to b plus LF square t eta square. Therefore, the smallest optimality gap achieved so far is given by f best of capital T minus f of x star less than equal to 1 over t summation from t equal to 1 to t f of xt minus f of x star, which is less than equal to b plus LF square t eta square divided by 2t eta. To get the oracle complexity bound, we need to equate this to epsilon. As we have already seen, there are two terms in the bound. Assuming that the two terms have equal contribution at the end, we can equate each of them to epsilon by 2, so that we obtain that eta equal to epsilon by LF square, and then t would be given by order of b LF square by epsilon square. So now, since epsilon dependent step size may not be practical, let us look at an adaptive step size rule called the Polyak's step size, which was proposed by Boris Polyak and is given by eta t equal to f of xt minus f of x star divided by norm square of gt if gt is not equal to 0 and 1 if gt equal to 0. We don't need to worry about the case gt equal to 0 because at that point we are already at the optimum. Note that here the step size depends on f of x star, which is generally not known. However, there could be some scenarios where it may be known, although x star may still not be known. And in those cases, you can use the Polyak step size. There's one such example that we will look at later, where you need to formulate a problem where f of x star is actually known in advance. Substituting this inequality in the one-step inequality we obtained that xt plus 1 minus x star norm square less than equal to norm square of xt minus x star minus square of the optimality gap f of xt minus f of x star divided by norm square of gt. And then we can use the bound on the norm gt square so as to obtain that the right hand side is less than equal to norm square of xt minus x star minus square of f of xt minus f of x star divided by LF square. At this point, we can carry out the telescopic sum to get that x of capital T plus 1 minus x star norm square is less than equal to x1 minus x star norm square minus 1 over LF square summation over t equal to 1 to capital T f of xt minus f of x star square. So let us carry this equation over. So in this equation, as usual, we can bound the term on the left with 0 and one on the right with b, so that rearranging we obtain that 1 over t summation over t equal to 1 to capital T f of xt minus f of x star square is less than equal to b LF square by t. So all we need to do is bound the left hand side with the minimum value and then take square root so as to obtain f best of capital T minus f of x star is less than equal to square root of b into LF divided by square root of t. Now equating this to epsilon, we can see that the oracle complexity bound becomes b LF square by epsilon square, which is exactly the same as the oracle complexity for the case when we were using epsilon dependent step sizes. Let us look at another step size which is adaptive but does not depend on f of x star. So let us consider the step size eta t equal to square root b divided by norm of gt into square root t. So this is also an adaptive step size, but it depends on the subgradient norm only. We are assuming that gt is non-zero, or else we would have found the optimum. So substituting that into the one-step inequality, we get that norm square of xt plus 1 minus x star less than equal to norm square of xt minus x star minus 2 times square root b by norm of gt square root t times f of xt minus f of x star plus b by t. So next we can carry out the telescopic sum so as to obtain that x of capital T plus 1 minus x star norm square less than equal to norm square of x1 minus x star minus 2 square root b summation over t equal to 1 to capital T f of xt minus f of x star divided by norm gt into square root t plus b summation over t equal to 1 to capital T 1 over t. In this inequality, we can lower bound the first term on the left hand side with 0 and upper bound the first term on the right with b. Also, we can bound norm of gt with lf so that we obtain that 0 is less than equal to b minus square root b by lf summation over t equal to 1 to capital T f of xt minus f of x star divided by square root t plus b times summation over t equal to 1 to capital T 1 over t. So this is the inequality that will allow us to bound the minimum optimality gap. Let us carry it over and rearrange it so as to obtain summation over t equal to 1 to capital T f of xt minus f of x star divided by square root t less than equal to square root b lf 1 plus summation over t equal to 1 to capital T 1 over t. We can bound the term on the left hand side by taking the minimum value so that we obtain that summation over t equal to 1 to capital T of 1 by square root t times f best of capital T minus f of x star less than equal to summation over t equal to 1 to capital T f of xt minus f of x star divided by square root t, which is less than equal to square root b into lf times 1 plus summation over t equal to 1 to capital T of 1 over t, so that we obtain f best of t minus f of x star less than equal to square root b lf 1 plus summation of 1 by t divided by summation of 1 by square root t. We have already seen the kind of sums on the right hand side before. Recall that we have seen that summation over t of 1 by t is approximately log of t and summation over t of 1 by square root t is approximately square root of capital T. So we have seen that how to calculate these sums using integrals. So substituting these, we obtain that f best of t minus f of x star is less than equal to square root b lf by square root t 1 plus log t, which can be roughly translated to the oracle complexity of order of b lf square by epsilon square log 1 over epsilon. So as compared to the other two step size choices, here we have an additional log 1 over epsilon term. So the oracle complexity is slightly higher. There are other choices of step sizes also possible. In the context of subgradient, because we are not taking the descent direction, practically you might see some oscillations, especially if the step size is large. One way to ameliorate that problem is to carry out iterate averaging. That is, for any step size eta t, we can use that x bar of t is equal to summation over tau eta tau x tau divided by summation over tau eta tau. So in practice, we can do this cheaply by maintaining the sum of eta t as eta bar of s equal to eta bar of s minus 1 plus eta t, and then maintaining xt bar as xt bar equal to xt minus 1 bar times 1 minus eta t by eta bar of s plus eta t by eta bar of s into xt. So now, since f is convex and x bar of t is a convex combination of the iterates xt, then we have f of x bar of t is less than equal to summation over tau eta tau f of x tau divided by summation over tau eta tau. So if you go back to the proofs, you can actually use this inequality almost everywhere and get exactly the same oracle complexity bounds for almost all choices of step sizes. So that is all for this video. We will continue in the next video and analyze the strongly convex case.